I'm going to start where we left off on the last session, but you'll notice a little bit of a difference in this form of the equation. This is the Friss equation, of course. On the far right-hand side, you'll see that I actually changed the term that was previously a lambda in the numerator, and I've replaced it with c divided by f, because we know that there's a connection between the wavelength, represented by lambda, and the frequency, and that's basically the speed of light. C equals the wavelength times the frequency. The only reason I did this is because it's often more common for communications engineers to think of this link budget in terms of maybe a frequency, a transmit, antenna and receive transmit, antenna transmit and receive frequency rather than wavelengths. So that can be a convenient way to discuss this. Everything else, just a quick recap, is that we're trying to solve for the received power at some distance d in the denominator on the far right due to a transmitter, which is represented by PT, and the two gain factors. That is really the focus of this part of the video. So the way we lead into this discussion about gain was to first talk about one of the major contributors of gain in this Friss equation is going to be coming from the antennas. And if we describe the gain of a receive antenna or a transmit antenna, it really makes no difference. They both have a part in basically amplifying that signal that's ultimately going to be decoded at the Earth's surface. If you remember in class, we went through some examples and some descriptions from this website here, and we started with this discussion of what a radiation pattern was, as basically defining the variation of power radiated by the antenna as a function of direction away from the antenna. And there's a lot more details that we can go through on this discussion, but we talked about how we have to be in the condition of a far field, and we meet that condition with the satellite communications example. We talked about describing things like decibels, gain in terms of decibels, and graphical representations of what that power distribution might look like. So we also talked about cut planes and how to take slices in a two-dimensional space to represent where maybe some of that maximum energy might be seen. We talked about azimuth and elevation cuts. And this led up to a discussion in how different antennas perform with respect to their radiation patterns. And another definition was directivity. And directivity, as we know, is a measure of how directional the antenna's radiation pattern is. And these are, definitions that we use to describe and compare different antennas. We talked about spherical coordinates and how an antenna's normalized radiation pattern can be described as a function, and then that directivity is related to that function with some integration taking place. We actually did this in class where we defined the directivity of a number of antennas that followed these different functions. So we can just plug those functions that describe antenna 1 and antenna 2 into the equation and come up with directivities that give us a measure of performance as far as preferred direction and where the maximum energy might be. So we can see how we can get analytical answers for these, and we can compare some basic antennas. So now we can look at all these different antenna types that go from low directivity, which means they don't tend to prefer a dominant direction, over other antennas that do prefer a dominant direction in space. So always imagine that 3D location of a vector where maybe the maximum directivity would be seen. So we can look at them in linear terms here as well as decibels. And we spent a good bit of time talking about that as well. So all of this was to say this gives us an entry point to the gain of the antenna, which is related simply by this equation here. So if we know the directivity and we know the efficiency of the antenna, that ultimately represents the gain. And as you've already guessed by now, that goes back to the gain that we've been describing in our Friss equation. So these quantities are directly related to radiation pattern of that antenna, and using all the different terms, including efficiency and directivity. So we talked about the decibel scale and dB watts versus dBi. What does the I stand for with these gain terms? It's very important to have a little bit of context on this. I stands for isotropic, which means it's uniform in all directions. So if I can give you an example from one of our other solvers inside of Electronics Desktop, these are generic antenna models, and this is actually showing you what we mean by isotropic. It's not an antenna that exists in real life, but it's often used, I should say, to reference the performance of other antennas. So if you look at the scale here, notice that it says linear, which means it's not a decibel scale yet. So this refers to normalized field density, which could be the same reference as a radiation pattern. And you'll notice that it's the same in all directions. So you can see my x and y and z coordinates here. If we were in spherical coordinates, you could pick any theta or any phi, and the value of the isotropic antenna regarding that field density is going to be the same in any location. That's really the definition of what of isotropic in this case. So if I were to change the scale, notice that in linear here, it says linear, the maximum value is the same value everywhere, and it's always 1. But watch what happens when I go to a dB scale. Then the pattern looks exactly the same. My color coding is still maximum at this red value, and then there's a minimum at the blue, which we can't see in this isotropic example. But notice how the 1 has simply gone to 0. It's just a reference because we have gone to a decibel scale. And if you keep in mind that the way to get a decibel scale from a linear is to take the 10 log of that value, and the log of 1.0 is 0. So by definition, 0 now is the maximum. And for an isotropic radiator, it's the same everywhere. It's just a decibel scale, and we can always recover the linear value by switching to linear. So we could do this calculation on paper, or we could use a little utility like I'm using right here. The other thing to keep in mind is that I mentioned that this is not a real antenna. It's an isotropic antenna. What happens if we change, this is still a parametric antenna example, but if I switch over to something like a half-wave dipole, which we know are real, we've looked at these in the past, then I can see that I can do the same thing. I can get my radiation pattern. I can see where its maximum is. In this case, the donut shape is going to be maximized in the plane, like we see here. And I can switch this scale, just like I did, from linear to decibel. And again, I'm normalized to that maximum value, which is going to show up as 0 in a decibel scale. What happens if I look at other antennas that are going to be important, to us with, maybe later on, I can look at something like a pyramidal horn, and they have very different patterns as well. So these are all, just references to power distribution, and there are numbers of ways to describe them. So hopefully that kind of gives a little context about, don't be worried about this dBi term. It's always just a reference to isotropic. And if we go through the tables that we had seen in some of the previous examples, we can recall that there were various directivities that were given for different types of antennas, and that's where these come from. So directivity is related to gain, so we will be seeing things either in dB or dBi, and we'll just plug them into our formula as we calculate the link budget.